Okay, so today I'm gonna solve another problem, which is that's pretty, interesting, cool context. So it's called evaluate reverse Polish notation. It's a medium difficulty problem. I would say it's actually more towards easy in my opinion, but there's much more harder medium problems, I think. But anyway, so Amazon has asked it a lot, so 12 times in the last 6 months. Then we have these companies, Google 3 times, Apple 2 times. Okay, so let's get started with it. So I'm going to read the problem statement and walk through the examples and go through the constraints. So the problem says the following: you are given an array of strings, tokens, that represents an arithmetic expression in reverse Polish notation. We will see what that is in a second. Evaluate the expression. Return an integer that represents the value of the expression. So we need to evaluate the arithmetic expression, which is an array of strings, and we need to then return the result of that expression. And then here we have the valid operators that we have are addition, subtraction, multiplication, and division. And then each operand may be an integer or another expression, right? The division between two integers always truncates towards 0. This means that if we divide, for example, 2 divided by 3, and then the result we need to return should be the one that is closest to 0. There will not be any division by 0, so we not need to check for this. The input represents a valid arithmetic expression in reverse Polish notation, so we don't need to sanitize if the arithmetic expression is well formed or not. The answer and all the intermediate calculations can be represented in a 32-bit integer. In Python, we don't really care, but for example, if we were using C or C++, this matters because like there's different types of integers to store integers of different sizes, like 64 bits or 128 bits, 32 bits, etc. And then, okay, this is our examples. We have our tokens. So this 2, 1, add 3 and multiply. So then we have here the output is 9. And of course, 2 plus 3 is 3 times 3 equals 9. And then we have a larger expression, and then we have here the same result and all of this. So there's one thing to note, like for example, the order of operations matters. So if I say math order of operations, and then here we have this, for example, which I previously opened. So yeah, so we have this, the parentheses. So it's basically, they have a hierarchy, right? So we first solve everything that's in the parentheses. Then after that, we solve all the exponents or the square roots. Then we have multiplication and division in the same order of priority, and then addition and subtraction in the same order of priority. So there's just a few important things here to note. So I'm just going to open up a Python terminal really quick. So if we were, for example, to do this 1 plus 2 times 3, well, there's no need actually to, well, just to maybe demonstrate that this Python works in the same way. So for example, here, if we have 1 plus 2 times 3, this should output 7, right? As here. Why? Because of course, you know, the order of operations. So we don't have any parentheses, we don't have any exponents, but we do have multiplication. So this will multiply 3 times 2, which is 6, and then we'll perform the addition. 6 plus 1 is 7, right? But if we do the same thing, but we, of course, put this in parentheses, it should be 9, right? Because we're first adding these, which is 3, and then multiply the result by 3. So 3 times 3 is 9. So one thing with the reverse Polish notation here is that, first of all, that the notation does not need any parentheses for as long as each operator has a fixed number of operands, right? In this case, I think it will always be 2. So, and then we can see here that this is a postfix because we still have the operands 3 and 4, and then the operator is after. That's why it's called a postfix. And then in the more traditional, I think it's called infix notation. So infix notation, yes. So is of course the common one we use, right? Like we're used to 3 plus 4. And then there's another one which is called the prefix notation. So instead of this the operands being after the operators, sorry, the operators being after the operands, it will be at the beginning, right? So that's another type of notation. Yeah, so the general thing here is that this reverse Polish notation is more commonly, or the way those arithmetic expressions that are in reverse Polish notation or in postfix notation, they are evaluated using a very simple algorithm. But the trick here is that it uses a stack data structure, right? With the LeetCode order, so last in, first out. So for example, they have here an example. So 3, 4, and then the subtraction operator. So first 3 is put into the stack, and then 4. And then we pop 4, we pop 3, and then we do this this operation, which is -1, and then we push -1 into the stack. And that's done as we are encountering these the operands and their operator successively. So that's basically the gist of the algorithm. So if I open a Jamboard, yeah, this is actually quite annoying because Google is discontinuing this app, and it's very funny because Google has a Google graveyard, a graveyard that I was seeing actually recently. It's funny because they're killing it right now, which is, yeah, quite sad. And then you can see all the projects they have killed over the years, which is insane. They keep killing it. I don't know. Yeah, 294 projects. So yeah, quite sad, but yeah. Oh well. So let's get to it. So if I have, I'm just gonna use this as a stack, and let's get this guy here. Just to walk through the example really quick. Okay, so here first, we would push this guy right into the stack, and then, okay, let's close this thing, and then we will push 1, right? And then we will encounter our current character now will be this operator. So, I mean, sorry, I'm getting kind of ahead of myself, but this here, we're gonna iterate it through a for loop, right? And then right now, like this will be the I index will be here, right? So of course, we're gonna push all these digits, which are gonna be 2 always, to the stack until we encounter an operator, right? That's our condition to push these characters to the stack will be until, or if none of them are an operator, basically. If we encounter an operator, that's when we start to pop. So then this guy will be popped up the stack, and then this guy will be popped up the stack. Then we will have an empty stack, right? And then here we will add them together, right? So in the end, this will become 2 plus 1, and then that will be equal to 3. And then, as the Wikipedia article says, the result we then push to the stack, right? Because we need to keep finishing evaluating the expression. And then now our index and the for loop is gonna be here 3. So then we push 3 to the stack. So we're gonna have these 2 guys. And then after that, we're gonna have the multiplication, right? That's gonna be at the last character in this character array. Would be this multiplication. So the same operation is done. So we pop this 3, then pop this 3 from the stack. We have this, and then we of course multiply 3 times 3 equals 9. So we have it here, and then we can push that 9 to the stack, and then to here. Yeah, and then we will return basically this element. So we return the first element of the stack. So that's basically it. It's a very, very elegant solution. It's very simple. And then we, of course, we don't need to have the parentheses, right? Just because of this, we don't need to, we don't need to like add parentheses in this expression or anything, because we're using the reverse Polish notation. So that's basically the gist of this algorithm. So we are gonna implement it right now. There's one little detail we need to take care of. So for non-commutative, right? So if we have the non-commutative, which are basically division, right? So we have division and subtraction, because then the order matters. So for example, if this here was let's say a subtraction, we would need to basically reverse the order, right? Of these elements, because it's not the same 2 plus, 2 minus 1 than 1 minus 2. 2 minus 1 is 1 and 1 minus 2 is -1. So that's what we need to take care of. But that's pretty simple. Okay, cool. So let's get started. So here we have, by the way, forgot to mention something very important. So as usual, like if it says solved, it's because I previously solved this before. So I'm explaining like the logic behind it, and I'm gonna basically recreate the solution from scratch here. Okay, cool. So we will start. So we will loop through this. So we can say for token in token. And then, well, we are gonna initialize the stack here. It's gonna be an array. Use the array as a stack. And then we're gonna say if token, okay, we're gonna also use a more elegant solution right now, which is a set. So we're gonna say operator sets. So here we're gonna store all our operators. And then we're gonna have addition and subtraction. So we're gonna say if token not in operator set, we're gonna of course push it to the stack as we saw in the Jamboard. Jamboard. Token. This just avoids us like having a long if statement, like if token does not equal this and if token does not equal that. So this is much cleaner. Okay, and then we ignore the rest. But of course, if we do encounter an operator, that's when we start to pop from the array. So we can, yeah, I mean, we can use a while loop as well. So while token or actually while stack -1 not in operator set. Okay, so basically this is saying that while the top of the stack, right, is not here. So basically if this, well, the top of the stack is a number, I mean, we can do this like this because it will always be basically will always be popping 2 numbers, right? So maybe there's no need to do it this way as well, or we can do it like this. So for I in range 2, we don't need the I actually, we can omit. We can say we know those are digits, so we will, let's say here, pop digits from stack, and then we can have our digits. will be strings. And we can say digits dot append and stack dot pop. Okay, so this should be eventually, if we have this example, we're gonna first push this and then this, so this will be 1, 2, right? Because 1 will be at the top of the stack and then below it will be 2, right? So this will be 1, 2. Eventually 1, 2. Okay, so we have our digits, and now we have to handle if this token is a non-commutative. So to flip it, so if token does not equal, or sorry, equals division or token subtraction, then we reverse the digits. Reversing in place. Yeah, well, yeah, we can, yeah, okay, let's use this one. I mean, you can also use this slicing shorthand like this. So anyway, doesn't matter. Okay, and then we will say we need to compute, right? So we need to like evaluate this thing. So we can create another function. So def compute, then we have here, and then we have these things as strings. And then, I mean, there's several ways we can do this, but so for example, let's say so, or operator. I mean, one option is like if we have like several if statements. So for example, if operator equals this, then we return A times B, right? So we can do this, and of course, like it will be a couple of if statements. Or another option is we have something cleaner, so we can say operators. They can be a dictionary, and then we can have these guys as keys. And then we can have like an anonymous function in Python mapped as its value. So we can say lambda, it's gonna be the name of the parameters here. We just list them, and then the corresponding function. So for example, this will be division, right? And then we repeat this. Shit, I submitted it by mistake as usual. And then we have plus, and then after that we have negative. So we need to also update these guys. Update these guys here, and then this. Okay, perfect. So that's yeah. So then we can pass these operators here. It's gonna be as dictionary. Okay, so now what we can do, so I believe we can just do, okay, result. We can say operators, and then we can say we can index that at operator, because that's going to be our string or our character. And then after that, that's going to be our function. And then we need to convert this int A and int B. Yep. So this is going to be, and this, sorry, this guy here. Okay. So we're converting these into integers, and then we return the result. Okay. So I think, yeah, this should work here. And then we can call it here self.compute, and then we can say digits, and then we say 0, digits 1, and then here we have our operator, which is the token, and then our operator, which we have up here. Okay, yeah, so I think we also need to, yeah, let's try like this. I think we also need to return, yeah, this will return an integer. Okay, this will return an integer, I believe. So, and then we need to cast it back to a string when we append the result to the stack. So string R. Okay. Cool. So let's, I think that looks complete. So let's test. Let's test this. Why don't I have all the test cases here? Okay. Okay. Let me return the first item of the stack. So let's run it. Invalid syntax. Where is it? Line 5. Ah, I have a point here, not a comma. So let's run it again. Oh, and I forgot the commas here. Okay, let's run it. Missing one positional argument. Where is it? 36. Okay. I think I have more. Yeah, I have more parentheses here. So let's run it. So 9 is not valid value for expected return type integer. Oops. Yeah. So I have to convert this into a integer because it's a string. So let's run. Okay. So this test pass. Let me just reset all test cases. I also want to try to combine this one with division as well. So let's run. Okay, invalid literal for int with base 10. Let me do something really quick. I'm just gonna delete this, leave this one here. So just simplify the test cases. Oh, okay, yeah, I see. So I forgot to do the truncating towards 0. So I think, yeah, I need to do this here. It will automatically do it if it's dividing. So we can run it and see. Yes. So reset test case. Let's run. Perfect. So let's do this. Oh my God, I submitted it by mistake. Okay, but it passed. Fine, let's resubmit it. Okay, 22. I'm wondering why beats not so much, not such a good runtime. Yeah, I mean, this always needs you to like click more times actually to it for it to like stabilize, but it doesn't really matter. 31. Yeah. Okay. Cool. So this is, yeah, so this is basically the solution for this problem. So yeah, maybe actually having this method is kind of overkill, perhaps. But I mean, we can leave it. Why not? I don't know if that will produce calling this method 10,000 times. I don't know if that will produce overhead, but anyway, it doesn't matter. I'm not gonna like do micro optimizations at the moment. So I think this is, yeah, I think this is fine. This is the basic idea of this. So yeah, cool. So that's it, and then I will keep uploading more, and that's it for today.